And slideshow. So I'm going to do an intro to Cosmos, kind of the Cosmos vision, and a brief overview of the technical stack with me, Billy Rennekamp. Again, who am I? So my name is Billy from Louisville, Kentucky, the home of bluegrass music, thoroughbred racehorses, and bourbon whiskey. So if you'd rather talk about any of those things, I'm always happy to do that as well. The Cosmos Hub team lead at Interchain GmbH. Previously, I ran the funding program at the Interchain Foundation. I worked on the wallet team originally at Tenement Inc. After that, I was a developer relations manager. And prior to that, I worked in the Ethereum space on early bonding curves, automatic market makers, NFTs. And prior to that, I was a full stack web development. Independent of that, I have a project called Clovers.network, which is generated NFTs, and an NFT gallery called Foley.app. And just about me, I love hackathons. So I got into the space by going to hackathons. I highly encourage you all to participate in hackathons that are happening all the time. It's a great way to learn and get involved in the ecosystem. So the agenda today, I want to go a little bit over the vision of Cosmos. And then, like I said, talk about the technical stack. We'll begin with Tendermint, then go into the Cosmos SDK, talk about IBC, talk about the various virtual machines, talk about the Cosmos Hub, and then we'll briefly go over some of the other networks. And then at the end, we can open up the floor to questions. Feel free to raise your hand in the middle of the presentation for questions or clarifications as well. I sometimes speak fast and don't want that to hinder anybody's learning process. So the vision of Cosmos. So I like to think that Cosmos is one of these three-tiered solutions to various problems, but it covers sort of three main areas that I think are really game-changing or sets us apart. And it approaches the problem of scalability in blockchains. We have seen experiments like Bitcoin and Ethereum, make really amazing things possible, but have real fundamental limitations in the various possibilities of, like, let's say, mass adoption, whether it's aspects of scalability, cost, security, user experience, etc. Cosmos sort of arose out of realizing that those problems would occur on those, even though they're like massively successful blockchains, still sort of categorize them as experiments. And I think a lot of the core developers on them would also, use that word experiment. And so the Cosmos vision sort of began in 2014, already sort of looking ahead to understanding that there would be those problems with these experiments, or when you start seeing those problems. And one of the problems that you've often discussed with various like newer solutions in the blockchain space is scalability. We like to think that the Cosmos sort of vision approaches the scalability by allowing vertical scalability as well as horizontal scalability. And the term vertical scalability is often used in talking about trying to increase the number of transactions per second that a blockchain can process. So Solana is often referenced as a huge sort of step forward in being able to process a very large number of transactions per second through some clever engineering, and roll-ups being another way to sort of increase the number of transactions per second to that are kind of being processed by mainnet Ethereum. And so Tendermint is a proof-of-stake consensus engine and protocol that was developed by inside the Cosmos ecosystem that is a sort of another category of increasing the transactions per second, the vertical scalability of blockchains. It is harkens back to sort of 70s research on Byzantine, practical Byzantine fault-tolerant consensus. And we'll go a bit more into this later in the Tendermint section. But just to say, it is a way to increase the number of transactions per second. However, there will always be a sort of physical limit at the number of transactions per second that are possible on any sort of given blockchain. And so we like to think that there's a solution in Cosmos for horizontal scalability as well. Let me just double check. Yeah. The way that all of these sort of three columns that I haven't even finished going through yet, scalability, sovereignty, and interoperability, are achieved are through a paradigm inside of the Cosmos space of application-specific blockchains. And I should probably just touch on that before I go too much more into these other three. But an application-specific blockchain is similar to a dApp or a smart contract that's on like a shared state virtual machine blockchain like Ethereum, except for instead of having a bunch of dApps, a bunch of smart contracts on a single blockchain, all competing for processing power, for storage, for transaction block space, you have essentially a single smart contract on an entire blockchain. So the whole blockchain is dedicated to serving the users of that one application, that one dApp. And there's a lot of really nice things that become possible when you do that, or become possible once you solve the other problems, which are, oh my gosh, is it really feasible to have an entire blockchain per application? Blockchains are hard to make, they need to be secured. And in the early days of the space, this just seemed like an impossible task for, there to be so many blockchains. Sort of the one blockchain to rule them all mentality. There would just have to be one that was really secure, and that is the only way that we'd be able to achieve the properties that we're all looking for in these application types. But through the development of Tendermint that I mentioned, application-specific blockchain frameworks like the Cosmos SDK, like we'll go into, and interoperability protocols like IBC, we believe that it is possible to have an entire blockchain for your own app, and that there's a lot of benefits that come to that really sort of justify that choice to go in that direction. And as I was saying, one of the first ones is scalability. Once you have an entire blockchain for your application, you don't have to worry about all of the different applications competing for block space, which is where expensive transactions come from on networks like Ethereum, because they use a gas auction system. So if you want your transaction to be processed in any sort of a reasonable amount of time, you have to compete with the other transactions by paying more or more inside of the gas auction. And so when there's a lot of competition, the price can go really high. However, if you were to reduce the blockchain to a single application, that would already remove tons of competition. Now, ideally, you still have an application that is so successful that even with just a single application on the blockchain, you're still running into scalability problems. If you're looking at Visa, who's processing whatever it was, 16,000 transactions per second or something, and that's all just for a single application, a money transfer application, you want to make sure that you're able to accommodate that as well. And so brings back the sort of vertical scalability. You still want to be able to transact in large quantities per block, but you want to have alternative methods for expanding that transaction per second, and that's the horizontal scalability. And so horizontal scalability is made possible through IBC, the interoperable protocol that I mentioned a second ago. So in this scheme of application-specific blockchains, it's all well and good that you get an entire blockchain for your app, but you create a new problem, which is that now these two different blockchains are on totally separate continents. There's a really nice feature of Ethereum that when you have a smart contract, it can call another smart contract. They have interoperability between those smart contracts. And sometimes people describe blockchains as sort of hardened APIs, or like APIs with integrity. You know that the API to this smart contract, which is each method that you can call, each query you can make, it's not going to disappear overnight, because most of the time those smart contracts are built in a way that are meant to be immutable. They will never change. And so it's not like Twitter changes its business model and it removes an API that your business relied on. If you're sort of composing different APIs to create a new service, you need to be able to rely on those APIs to exist for your new idea to sort of continue. And this is the concept that's often referred to in the space as like money Lego blocks. It's the composability of these different applications that really sort of have compounding value, the sort of explosion of possibilities, because you have reliable building blocks. So once you have these application-specific blockchains, you miss out on being able to have these synchronous transactions between the smart contracts. And so the solution there is an asynchronous transaction type called inter-blockchain communication, IBC. And it's essentially the same thing as two smart contracts talking to each other. You can either execute a method on another smart contract, or you can query some state on another blockchain, except for it's done over a new data packet. So if you're familiar with the traditional internet, HTTP, et cetera, TCP, IP, you've got these packets of information that are relayed over copper wires or whatever sort of infrastructure, and received at different machines and processed in that way, and sometimes forwarded on until a destination and then responses are made, etc. IBC is really based off of a very similar model of TCP/IP, and it's where you package some information from one blockchain and you have it shipped over to another blockchain via a relayer. It's relayed there, and that other blockchain is able to understand and process that information. And when that becomes possible, you have horizontal scalability. So your application is running into its maximum limits of transactions per second. Well, now you can just deploy another instance of that application, and you've doubled the amount of transactions per second that are possible. And these two applications can still maintain synchronicity and state by sending and receiving messages over IBC. The next big column is sovereignty. And the sovereignty aspect is, I think, undersold in certain moments. So mostly when people talk about Cosmos, they're like, oh, cool, I need to scale my blockchain. I'm ready to take the world seriously. I'm ready to have an application that can meet the demands of my in-demand product. But what is really beneficial about having your own application-specific blockchain is that blockchain is custom fit to do exactly what your application needs to do. And so it's not that you are competing with all of the other dApps on Ethereum to say, hey, it would be really great if you could change the gas price of a transfer to this, or hey, it would be really great if you could modify and allow people to sign transactions with a different cryptographic curve, or all the other sort of parameters or features of a blockchain. They have to be one size fits all on applications like Ethereum. Whereas when you have an application-specific blockchain, you can change any feature of that blockchain that you'd like to meet the needs of your application. And so this sovereignty sort of aspect is the for us, by us, the FUBU sort of thing. But it also means that you won't have conflicts in the same way that you've seen on Ethereum. For instance, when the Ethereum Classic blockchain emerged from an argument that occurred on Ethereum after a hack took place on a large smart contract called the DAO. Nobody could agree on whether or not that hack should be rolled back or not, and so the blockchain split. But it's basically an example of having a bunch of different people who have different ideas about what the blockchain is, or what it does, or what it's for, and it's very hard to keep all those people in agreement all the time. However, if you narrow down the scope of what your blockchain does to a single application, it's much easier to sort of get agreement and maintain a continuous idea of how that blockchain should operate and what it should do. It's a simplicity, it's a separation of concerns, it's a way for the blockchain to sort of have integrity in a continuous life that doesn't have the sort of risks that come with these shared state virtual machines, conflict of interests, and inability to decide on exactly how the blockchain should function in any given moment. Interoperability is the other sort of column that has been brought up in each of those previous two, so I don't need to say too much more about that, but it does have this nice feature of separation of concerns. Each blockchain in the Cosmos space you'll see is often dedicated to a specific application, specific purpose. And if you're sort of familiar with a lot of the way people sort of talk about building successful products, it's about being laser focused on exactly what your product does for exactly what your users' needs are. And it can be really, really difficult to make a successful product that tries to do too many things at once. And so just sort of a nice feature that occurs from this separation of concerns with interoperable application-specific blockchains is that you're able to sort of dedicate your application to a very sort of specific and lean purpose that helps keep it on track. So that's kind of a meandering path through some of the more important ideas, I think, about what makes Cosmos different, or where the sort of values and the vision of Cosmos are. I know that this slide doesn't include most of the sort of things that I actually just went into. Before going into the sort of Tendermint, Cosmos SDK, and IBC protocol at a lower level, is there anything related to the sort of larger vision that anybody would like to stop me about? I can't see anybody's faces right now, so I'll just wait 5 seconds, and unless somebody speaks up, keep going. Okay, I'm going to keep going. So Tendermint was the first piece of technology that kind of came out of the Cosmos ecosystem. It was begun in 2014 by Jay Kwan and quickly joined afterwards by Ethan Buckman, who wrote his master's thesis on the protocol. And it was originally thought of to be used for enterprise blockchains, but very quickly they realized that the possibilities of having proof of stake scalable blockchains was much larger, and the sort of Internet of Blockchains vision came about that I just mentioned, the sort of application-specific and interconnected blockchains. But Tendermint itself, as I mentioned, said a second ago, is classic BFT, Byzantine fault tolerant, which means that it is a bunch of disinterested third-party actors who are all coming together to try to come to agreement on the state of something. And the Byzantine generals problem is referenced as a computer science scenario that has the same properties, which is, Byzantine generals problem came from talking about a large battle that was being a siege on a castle or a town in which it was completely surrounded, but because there was not cell phones in the time, they had to run messengers from each commander to commander. And if the army were to all attack at once, it would be successful. However, if only part of the army were to attack at once, it would all fall apart. And so the army needed to figure out when they were all going to attack and get on the same page about the plan. So they had to come to consensus about that plan. And the idea is that the army actually has some spies and some Byzantine actors, some people who are actually trying to help the city instead of the army. And so when they're asked to run a message to the other commander that says, hey, we're going to attack at dawn, they would specifically not run it over there, or they would change the date. And the idea is that as long as the army has at least 2/3 or 1/3 honest scouts running this message back and forth, there would be different guarantees about the group being able to come to consensus. So hey, I got one bad message, but I got 2 good messages. That sort of logic that would eventually sort of make the entire group come to an understanding of what the plan is, the consensus. And so this computer science problem was solved in the 80s, but it was expanded to a set of participants much larger than you typically see in sort of database syncing, which is what consensus was mostly used for before. And that is exactly the properties necessary for a large decentralized network like a blockchain. So it was a continuation of school of thought, but one that was sort of supercharged to be viable for these application types. It uses what's called proof of stake. So Tendermint is consensus, meaning it says, hey, we want to all come to agreement. And I heard some information from over here, and that information came from somebody who's you could say credible. We use the term voting power. So this person has a lot of voting power. This person has a little voting power. And you need to get a threshold of voting power. That's the 1/3 or 2/3 to say, okay, now I think that we've all come to agreement or not come to agreement. And the way that you can translate voting power to a blockchain is proof of stake. So I could say I'm going to lock up a bunch of money, and that translates to some equivalent voting power. If I lock up 1/3 of all the money on the blockchain, I get 1/3 of the voting power on the blockchain. Is roughly the way we sort of roll out most of your proof of stake systems. It's technically a delegated proof of stake, which means that I'm the validator who's proposing a block, and it's not only the proof of the stake that I've allocated, but all of my delegators. So anybody in the blockchain is able to basically delegate money to me. That gives me authority on participating in the consensus. And once you have that authority, you basically go through a round robin. So all of the validators get to have their turn producing a block. And the frequency of how often they get to propose a block is determined by how much delegation, how much voting power they have. And again, that voting power is just a translation of how many tokens have been locked up. So an interesting feature of Tendermint is that it's modular. So Tendermint is the consensus. It's an entire system that's just about trying to come to agreement about what's inside this block, what are the transactions in there, what is the hash of the application. But then there's a separate application running, and that's the actual app itself. That has stuff like, who are the users of my app? How much money do they have? What are the things that they do on this application? And these two processes run in parallel. The way that they speak and communicate to each other is a protocol called ABCI, Application Blockchain Interface. And I mean, this whole course, you're going to be going much deeper into details about all this, but it's good to sort of have it prick your ear a little bit this first time, I think, so that later on when you're reminded of it and you're going deeper, you're like, oh, that was the time I heard about ABCI. But ABCI is essentially the way that these two processes communicate with each other. So once they've come to consensus on a block and all the transactions, Tendermint will hand that block over, ABCI, to the application, and then that's when all those transactions are actually executed. There's a couple other communications that take place, sort of like before the block is produced. Tendermint will be like, hey, I think this transaction looks okay. You think it looks okay? The application will be like, yeah, put it in there. I'm sure it's fine. And then when they're all finished, they'll hand it back. And there's a few other things. And the communication protocol between them has actually been expanded recently to do things like application ordering. So if you're familiar with minor extractable value, the ability for the block producer to sort of order the transactions before they're included in a block. These are the sorts of queries that happen and communication that happens between the application and Tendermint, who's actually in charge of putting them into a block. That's what the check-TX example there is about. Which brings us.
Sorry, I think we do have a question, if it is okay with you.
Yep. Is it text? Because I can't see the screen right now.
No, it's a raised hand from Mr. Kosick.
Yeah.
Go ahead.
Question. I was reading the first week of our course, and I also heard you say about 2/3 of the things need to be upright. Like I was reading through it, and it said that for everything to function correctly, at least 2/3 of the things need to be working correctly. So why is it 2/3, and why is it not more than 50%?
So in different, depending on what you're asking for, it's 2/3 or 1/3. And sometimes I'm rusty on exactly the difference, but for 2/3, if you have 2/3 honest majority, you can guarantee that there's no censorship. And if you have 1/3 dishonest, so if you've only got like 1/3 of honest actors, then you've lost the ability to guarantee that censorship isn't occurring, which is similar to the idea of losing 2/3. So let's roll back for a second. We've got a network running, 100% honest validators. Everybody's happy, everything's good. Now we've got a network and there's 1/3 plus 1 bad guys out there. What they're able to do is they're able to prevent transactions from being gossiped to everybody. And so this is like the battle scenario. I'm a spy. I don't want the message to get to everybody. I can't change the contents of the message, but I can prevent people from getting the message. And so that's like not a great quality for a blockchain. If you want to have a censorship-free blockchain, you need to make sure there's at least 2/3 honest participants. They can't make the blockchain stop running if there's only 1/3, but they can prevent transactions from being included, you know. And where that becomes really important is if, for instance, there was a misbehavior, somebody was doing something really sketchy on the network, either through consensus or there's other sort of conditions that you can be slashed for, and that person had 1/3 control over the network or had colluded with 1/3 who was willing to sort of orchestrate this. When you want to submit that evidence to the blockchain and slash that person for doing that bad thing, they are now able to prevent you from submitting that evidence that would harm them. And so 1/3 bad actors is already like a pretty bad state. However, it takes 2/3 of bad actors to actually like halt the blockchain and fork it or do sort of like the more severe bad case scenario sorts of things. And you should look into the actual algorithm of Tendermint and PBFT to understand exactly why it's 2/3. I feel like I remember at one point it was about half of half meeting with another half of another half to do something, but it escapes me right now. It's in the sort of like proof and formula. Tendermint's been formally verified and proven, so there would be some math that will extract those numbers, but off the top of my head, I can't give you the reason why the numbers shake out that way instead of as 50%.
Okay, thank you. That is all.
Blow my nose and get back into it. So we're into the Cosmos SDK. We like to think that the Cosmos SDK is kind of a Ruby on Rails for blockchains. But what's important to point out is that the Cosmos SDK is just one software development kit for building application-specific blockchains. Excuse me. In earlier days, there was another SDK also written in Golang originally made by Ethan Frey, the author of Cosmwasm, who you might be familiar with, and we'll talk about later. Excuse me. That was a framework called Weave that the first version of, I think, Region Network was built in. There's also a JavaScript framework called Lotion.js that was made by the creators of the Nomic blockchain, who are now working on a Bitcoin bridge. There's also a software development kit written in Swift. There's a software development kit called Orga, which is in Rust. Although I hesitate to call it a software development kit, it's more of like a library for building blockchains in Rust. The Polkadot software development kit is called Substrate, which is a Rust framework for building application-specific blockchains. Their framework can be used to make Cosmos chains that use IBC, thanks to a recent development of building IBC into Rust. However, most of the Substrate framework is built in a way that it expects the Polkadot parachain to be running, which is a different sort of way of securing networks and organizing the topology of application-specific blockchain networks. So you would need to make sure that Substrate satisfies your other needs before approaching it as a sovereign blockchain. But like I said, there's sort of like many different ways to build application-specific blockchains, and the Cosmos vision is meant to embrace all of them. While just being practical and getting from 0 to 1, we found it important to build a world-class software development kit to make building application-specific blockchains as easy as possible, which is why so much time and effort has been put into the Cosmos SDK. So while I think it's a world-class application software development kit, the vision is really not limited to the Cosmos SDK in any way. It's a SDK built in Golang, and it uses a modular system. It tries to abstract things into separate areas so that you can build a blockchain really fast. There's a CLI system called Starport, which is sort of like or Ignite, which sort of demonstrates that you can launch a blockchain in like 5 minutes or something like that, just by adding the right parameters for which modules you want to use. But when you're actually building a custom application, you're probably going to have to build your module with a lot more foresight or involvement, let's say. But the SDK comes with a bunch of standard modules that we would expect most blockchains to want to use. That's stuff like auth, which is an account abstraction module. So basically, if you're thinking about it Ruby on Rails, this is like your users module. Hey, my application is going to have a concept called users. Let's get that. Then we have the bank module. And so that's like, hey, my application is going to have the concept of tokens or coins. I should import the bank module. It's got the gov module. So if you want your application to have the concept of using some token to vote on some things, then you'd want to import the gov module. And then staking module is a pretty standard one. This is, like I said, the way that you translate tokens into voting power for Tendermint. So Tendermint's going to ask your application, hey, who are my validators and what are their voting powers? And your application can decide that list however your application wants to. Maybe you want to have a proof of authority application that doesn't use proof of stake, but actually just says, hey, these are the 10 people who are allowed to produce blocks, or these are the 100 people that are allowed to produce blocks. And they are going to be changed by an admin, or they each get one vote or something like that. So they all have equal voting power. That's what a proof of authority set looks like. Tendermint doesn't care. They just say, hey, tell me who the validators are. Tell me what their voting power is. It's your application that decides. And so if you want the standard proof of stake system, then you'd import the staking module. Staking module is part of a configuration that also includes minting and distribution, which is where sort of new tokens are minted at every block. And those block rewards are distributed to the people who produced that block or their delegators, which is what the distribution module does. So that's kind of like a standard configuration of modules that most of Cosmos SDK blockchains import. And then IBC. IBC is a standard module, and that's it's basically your network card. If you're looking at the metaphor of every application-specific blockchain kind of being like a single computer. IBC is your networking card. It's the one that lets your computer connect to the other computers, meaning your blockchain connect to the other blockchains. And inside of IBC, it has different applications. So IBC is the protocol that lets them talk, but the types of packets that get sent back and forth will depend on what kind of information you want to send back and forth. The first and most obvious sort of information that blockchains want to send back and forth are tokens. So that's what the IBC transfer module is. There's a number of other IBC modules at this point, but we'll go into that a little more detail later. The architecture of a blockchain, so like I said, we try to separate it out. There's essentially an app.co, which is your sort of like home file that just lists all of the modules and all the features that you want inside of that blockchain. It's where they're all tied together. You're mostly importing your standard modules that I just mentioned. And then you might import one or maybe two or more custom modules. And those are usually defined in the same code base under the folder X, where you actually have the meat and potatoes of what does this blockchain do different from all the other blockchains out there. And then there's a section of client implementations. Most Cosmos SDK chains come with CLI built into it, as well as gRPC and REST endpoints for communicating and interacting with that blockchain. Within each module, they're also broken up in sort of sections. So you won't have to deal with this if you're just trying to, like, say, make a clone of another blockchain that exists. You would just import the same modules that blockchain exists, and then maybe change the Genesis file, which includes like who has tokens at the beginning. But like I said a minute ago, theoretically, if you're going to make a new blockchain, it's probably going to do something specific and new. And so you'll make a custom module, and inside of there, you'll define which messages does this module have, what are the actions that this module enables, and similarly, what are the queries that this module has, what are the things that this blockchain will answer if it is asked by other modules. Messages are handled by something called a message handler. I think it was recently updated actually more to the message server system, but we don't need to get too in the weeds on that. Similarly, queries have a querier or query handler. They all sort of direct you down to the keeper. The keeper is where the sort of database level of each module is. It's a KV store, a key value store that can handle reads and writes that are namespaced by the module itself. And those can be shared between modules. So if I'm in the bank module, for instance, and I want to check out what type of an account I'm storing money for, I would import the auth keeper from the auth module and then say, cool, there's a user who has a multi-sig. I'm able to tell it's a multi-sig because I ask the auth keeper, hey, the account address so-and-so, what type of account is that? Oh, it's a multi-sig account versus, oh, it's a private key account versus it's a groups module account or some other sort of module-based account. So there's account varieties, and that information you'd be able to access by importing the keeper and doing a read inside of it. So IBC protocol, often described, I like to call it kind of like a bridge in a box. So if you're familiar in the blockchain space, bridges are a big topic. For the reasons I mentioned before, people are realizing that it's not going to work just to have one big blockchain that we all happily use all the time. So we've seen, a real explosion of blockchains out there that all have different features. I think we're still seeing people try to minimize the scope of shared state virtual machines. So, hey, this is going to be a DeFi Ethereum chain, and so that way we're going to reduce, the types of applications there, or Polygon is making a play for a lot of, say, game developers, or you start to see differentiation in like what type of Ethereum clone, and that's a way to sort of address the sovereignty and scalability issues. But we expect it's only going to continue down the road to hyper-specific, application-specific blockchains. But regardless, we've seen this need for communication between blockchains and a plethora of bridges and a plethora of bridge attacks. Most of these bridges are composed of a group of kind of validators or participants or people who are like supposed to operate that bridge. IBC is a bridge in a box because it reuses the validator sets of both of the sides of that bridge to be in charge of providing proof that this bridge is being run correctly. So it sort of has the highest degree of integrity that's possible in a bridge architecture. And it does that by providing light client proofs of the state of each side of this blockchain. So you're no longer relying on some group of middlemen who are looking at each blockchain and saying, yeah, these tokens were locked up over here. Trust me, you can mint them on this side. They've been locked properly. Or the other way around. Oh, you want to move tokens back? Cool, these tokens have been burned. You can unlock them on this side. That's how most bridges work today. And instead of having that group of middlemen sort of decide that, IBC says, I don't trust you. Give me the real data. Give me the data on that side of the blockchain that proves to me that this action actually took place on that other blockchain. So it's all of the sort of best features of a bridge without any of the sort of trust assumptions. And what's great is that you can just sort of spin it up if you already have a blockchain, because you already have all of the necessary pieces. So you import that module, and all of a sudden you've got a bridge running without asking for permission, without giving permission to anybody besides the network itself. And the shipping container is often used as a metaphor for the packets of IBC. And the reason is because IBC is broken up into multiple layers, the transport, authentication, and ordering layers. And so you can think of the shipping container, which is used in international trade to move goods around the world, is really successful because the whole world agreed on the dimensions of this shipping container box. You know, you've seen these like giant cargo ships going across the sea that are stacked with them, you know, perfectly all in line. And they're a bunch of different colors because they're produced from different makers all over the world. But as long as everyone agrees that they're the exact same dimensions, they're going to work really well together in this international shipping system. However, that doesn't mean that the shipping container knows or cares about what's inside of the boxes, or knows or cares about where it's going or who sent it, etc. As long as the shipping container follows the rules of its dimensions, it's able to participate in this larger global trade system. And so IBC is built in a similar way, where at each level, it's sort of standardized but swappable depending on how the dependencies work. So the actual packet, you know, doesn't know what's inside of it. It doesn't know who's sending it or who's receiving it. It's just built in a standard way so that it can answer those questions in a reliable manner, no matter where it is or who's asking. And so the transport layer is basically, you know, the ships and the big trucks and the cranes that move around these packets. You know, they don't necessarily need to know what's inside of them. They just need to be able to read the label that says, where is it going, who's receiving it, and like, did they pay to have it shipped, basically. And so what's really nice about the relayer system is that this is also trustless in the sense that, you know, I've decided to send a packet from blockchain A to blockchain B, and I've attached, you know, whatever necessary fees to get it there. I don't need to go and ask somebody to move it for me, and I don't need to give permission to somebody to move it for me. Anybody in the world is allowed to see that there's an outgoing packet on blockchain A and move it to blockchain B. And so there's this new sort of industry of what are called relayers, and it's people who are competing to transport that packet on behalf of the sender. Technically, the sender could transport it themselves, because all you need to do to transport it is to have an internet connection and an account on both of those blockchains. So there's sort of many ways that we can make sure IBC packets get transported and continue to move across this sort of network. But it's especially opened up because it doesn't have any requirements about who's allowed to move it. Authentication is the next layer, and this is the sort of like give me proof layer. So if we're using this shipping container metaphor still, this is the you know, the shipping label, let's say, that says, hey, this came from so-and-so, it's going to so-and-so. Here's the signature of the person who sent it. You know, here's the receipt for the payment contract that paid for the whole thing. You know, this is like where I get the integrity that the contents of the ship is really coming from where it says it's coming from. And the way we do that in blockchains is with light clients. This is the sort of highest degree of proof that the contents of a IBC packet came from where it really said it's coming from. And the way that works is that you've got two blockchains and they've got a consensus mechanism. And a light client is just a way of saying, so when you've probably heard light clients in the term with like full nodes, light clients, and generally it's thought of as a piece of software. A client is like a piece of software that's used to run a blockchain. So you don't necessarily have to participate in block production to run a node on a blockchain. It's a really important thing to do for networks to make sure that there's a lot of accessibility, et cetera. If you want to have really high integrity or privacy, you might run your own node and submit the transactions locally and then have it propagated over gossip. And so, the idea of like running a client of a blockchain is just basically running an instance of that blockchain. A light client is referred to as an instance of running a blockchain that tries to cut corners or do the most efficient way of sort of proving that this application is current with the whole network and correct according to the whole network without having to run through every single step of running every transaction of every block. And so, for instance, you can, there's all these sort of like clever methods that people realize that you can skip, half of the blocks over the last whatever blocks. And as long as the hash hasn't changed to beyond this degree of something or another, then it's still considered safe, or at least, impossibly small of a margin of error through the cryptographic math that says it's probably still part of the same network. So there's a whole category of these like tips and tricks that compose light clients. And what IBC does is it will run a client of a different blockchain within its own state machine by using a light client. So I've got blockchain A and there's blockchain B. Without light clients, blockchain A would have to run an instance of blockchain B inside of its state machine. So if you know Ethereum at all, you know that like running any processing inside of a smart contract is very expensive. So if you were to run an entire virtual instance of another blockchain inside of a Solidity smart contract, it would take tons of processing. You'd have to include everything that happens on this blockchain inside of this blockchain. That's tons of extra sort of processing. So it'd be really expensive. However, if you were to reduce the duty of running that whole blockchain down to a light client that's extremely efficient, it would decrease the amount of work you have to do on this side by a ton. It would still be infeasible on Ethereum mainnet where processing is so expensive, but on a blockchain like Cosmos SDK chain, it actually is totally feasible. So each of these blockchains runs an instance of the other blockchain on it, but that instance is a light client instance, which is, like I said, a much more reduced requirement of running every transaction. And so each of these blockchains basically knows what's going on in the other one. And periodically they send what are called client updates to each other that says, hey, we haven't talked in a few days, but like since we last spoke, here's some updates about my blockchain. And just the updates that are relevant enough for you to keep your light client update. I'm not going to tell you every single thing that happened, just the stuff that'll give you like the integrity and the proof that like, I'm basically where I say that I am. So as long as these two blockchains keep up to date with each other's light clients, which needs to take place at a minimum every 2 weeks, which is sort of the bonding period and the period that like they would diverge enough that they would maybe actually not believe each other's light clients anymore, then they're able to stay in sync with each other. And as long as they have a, as long as they have a sort of understanding of the other blockchain's state via their light client, they're going to be able to accept IBC packets from each other that contain things like token transfers or any other sort of contents that would go inside of those shipping containers. So like I said, the token transfer is sort of the most basic and obvious one and the most widely used one. When we have these two blockchains and user A wants to send tokens to user B on the other blockchain, this desire to send tokens is recorded inside of an IBC packet and it's sent over to this other blockchain. Now the header on that IBC packet, the shipping containers label says, hey, here's the information about this token transfer, and here's the latest headers from my blockchain that prove this content actually was part of the state machine, part of the application hash that you have a sort of continued understanding of. So this blockchain will look at that information, look at the previous information it had about that other blockchain, be like, oh, you're right, I can tell that this really came from that blockchain. I'm going to accept it as valid, and I'm going to print these tokens over here, which were locked up over here, and give them to the user who they were sent for. And that's sort of why it has such a high degree of integrity, because it really understands what's happening on each side of those blockchains. You're not trusting any PID in the middle. Another way to sort of prove that something came from the other side is what we call a solo machine. So like I mentioned, IBC is super modular in that you can sort of swap out different pieces of it that have different reasons for existing. So while a light client is sort of the highest degree of integrity, what's really happening is there's a section on that label that says proof. And typically the proof will say light client proof. However, you could put a different type of proof, which is just like, I called a solo machine. And that I said so, has a lot lower degree of trust. Oh, okay, I'm supposed to trust who sent this just because you told me so. But if that's enough for me, then I'm willing to accept it. So in an instance where I might like run a WordPress, and I want that WordPress, which is completely controlled by me, it's not a decentralized network, but I want that WordPress to interact with the Internet of Money, that WordPress could technically create an IBC packet, and it's signed by me, Billy Rennekamp. Maybe it's just my private signature, and it can be sent to the Cosmos Hub or somebody else. So if I've registered on the Cosmos Hub that says, hey, I'd like to register as somebody who can give proof for IBC packets, I can do that. And then the only proof that I need to provide is just a signature from Billy Rennekamp. So it's a lot lower trust, like a signature from me is just some random guy that says, hey, I have an instance of a blockchain and it wants to talk to you, and he's sending tokens to you. Like, okay, cool, we got your tokens, but like they're only backed up by the signature of one random guy compared to these tokens, which are backed up by an entire consensus mechanism, an entire blockchain. IBC doesn't care. It lets the users decide, should I care about these tokens that came over because some guy said they exist, or should I care about these tokens which came over from like an entire blockchain that I'm familiar with? Really doesn't matter. There's a lot of reasons I think that you would actually be able to have important use cases when just one person says, okay, these tokens came over. Like for instance, crypto.com, which is a centralized exchange, they have a trusted bridge, and all they need is just like basically a signature from their trusted partners. So they're able to use the IBC solo machine, still use all the other benefits of IBC, but not have a consensus mechanism that's giving proof. It's just saying, hey, somebody who has authority to send this shipping container has asked to send it. IBC doesn't care, they'll send it anyways. The person who receives it has to decide, do I want to do anything with the contents of this based on the fact that it's only signed by a single random guy that I do or don't know. The other aspect of IBC is the ordering. So this is the part of the protocol that just says, hey, somebody was meant to send 3 shipments of goods. The third shipment came before the first shipment. Let's wait until the first shipment comes before trying to unpack the third one, because sometimes the data is too much for a single packet, so it gets added to multiple ones, or sometimes the actions are really important to be processed in order. So that's the other sort of feature of IBC that's part of the stack, is whether it's ordered or unordered. Related to that is sort of timeouts. Say packet 2 comes, packet 1 never comes. After waiting for so long, I might just say, okay, you know what, call the whole thing off. Send a message back to the sender and say, hey, we never received packet 1, and now it's timed out, so you're gonna have to restart the whole thing if you really want us to do it. And that's the ordering part. So this is really similar to TCP/IP, and all of it is sort of like cryptographically backed up by these different methods of authentication. Mentioned TCP/IP, so there's this handshake that sort of takes place at the beginning where each of these blockchains are sort of telling each other they exist, and that's where they sort of say, hey, this is the light client that I use. Do you have an instance of that light client? Here's all the stuff that's happened since I was born that will give you an idea of who I am and what the current state of my application is, and that'll allow you to further process future packages or future packets that include IBC token transfers or other application layers. So without going too much into that, I know we're getting close to the hour.
I think we have a question, Billy.
Oh, sure.
Sorry to interrupt. Bradley, go ahead.
Yeah, I was just wondering if the Cosmos SDK supports multi-hop IBC packets yet.
Yeah, so multi-hop can occur in a couple ways. The most basic way that you'd expect is, say, I have 3 networks, and I want to send tokens from network 1, so no, network A to network C. However, for some reason, I don't want to send them directly from A to C. So I can send tokens to network B with information about the destination on network C. That's currently possible with what's called the packet forwarding middleware module built by Strangelove and included on the Cosmos Hub in Gaia for the last year or so. However, like I said, there's like, if for some reason you'd want to send it through there and send it directly, brings up this question, why wouldn't you send it directly? When you send it directly, it's only 1 hop, which means that it's half of the price in terms of the fees, even though the fees are minimal, and the latency is lower because then it goes to the destination just slightly more faster. So there's this question, why would you go through a middleman when you could just send it directly? And there is a reason to do that. but it's mostly around support for the job of relayers. So in a world that you have, thousands and thousands, if not hundreds of thousands or millions of blockchains, similar to the way that there's, millions of computers on the internet, it's impossible in terms of topography for each of those computers to be connected directly to each of those other computers. And so we see a hub and spoke model in which many computers are connected to these hubs. Those hubs are sometimes connected to other hubs, and that creates the path for routing packets between a source computer and a destination computer. So that way that source computer and destination computer don't need to be directly connected. With regard to blockchains, that is mostly a burden on the relayers, who are the participants that have to keep those connections directly open between all those different networks. And so it drastically simplifies the life and the burden of a relayer should there be this hub and spoke model where, okay, instead of me sending from blockchain A to blockchain C, or theoretically from blockchain A to blockchain Z, and everyone in between, I'm just going to keep one connection from blockchain A to blockchain B. That's really simple to keep that connection alive and keep it running all the time. And then I can add information about blockchain Z because blockchain Z is also connected to B. Once we're at the level of complexity where that's necessary, multi-hop makes a lot more sense, which is why we've implemented and deployed that module already, but it's not super widely used. The other important part about multi-hop is that every time you make a connection between two blockchains, they're making a trust assumption about those light clients. It's saying, hey, light client has a 99.99% degree of integrity or whatever, but there's still that 0.1. I want my light client to have more integrity or less integrity, which means that I need less or more evidence, depending on like the parameters of that authority or that proof that you need. There can be different connections between two blockchains. So for instance, there could be two blockchains with two connections between them. One of them requires very little proof for the light client, and one of them requires tons of proof for the light client. Technically, those have two different trust assumptions, and one of them could be corrupted while the other one is still correct, which means that the tokens and the packets that are sent through those different things have different properties as well. And the way that those properties are seen is through the denomination that came through. So if I'm on blockchain A and I send my token through two different channels, those two tokens are no longer fungible because they represent two different trust assumptions. So the same goes for when you have a topography of 3. If I send tokens between blockchain A to B and then B to C, those are different blockchain A tokens compared to the ones that were sent directly from A to C, because these ones took 2 hops and these ones took 1 hop. So those are different token types now by the time they've landed there. And so we're getting ourselves in a kind of a problem where we're using all these pairwise connections between blockchains because they're faster, have lower latency, and it's still possible because we don't have thousands or hundreds of thousands of blockchains yet. But when we do get to that point where we want to start multi-hop routing, we're going to make a division of denominations. There's going to be all these ones that were directly connected and all these ones that went through multiple hops. And now they're no longer fungible. And so the second degree of multi-hop technology that's being worked on by the IBC team is to have a update to IBC so that you can have like a pass-through trust assumption, so that tokens which were sent from A to C directly look like they're still connected directly, but the actual packet is able to be passed through B and then to C. So when C receives it, it says, cool, I got this from B, he got it from A, but I'm going to pretend that I got it directly from A because I trust B. And that way, the tokens that are transferred are going to remain fungible together. And so that's still being worked on, doesn't exist today, but it's the way that we're looking towards future-proofing the need for multi-hop routing. Does that answer the question, Bradley?
Yeah, thank you.
Sure thing. I saw a couple text questions coming up. Should I start jumping into those?
I think that's a good idea to maybe start off the conversation.
Sure. Let me just make sure on the presentation, so we don't need to go. These are the different IBC application types. There's a token transfer I mentioned. There's interchain accounts, which we shouldn't go into because it's a whole conversation. NFT transfers are around the corner. And interchain security, cross-chain validation is a way to have one validator set secure 2 different blockchains at the same time. Oh God, I'm only like halfway through the presentation. Virtual machines, I'll just run over the end and then we go straight to the questions. Virtual machines, these are like having the EVM inside of a blockchain. There's different versions of it, some written in Rust called Cosmosm, some written in JavaScript called Agoric. Ethermint is the Ethereum virtual machine module. It's live on networks like Evmos. Looks the exact same as normal Ethereum, except for it's run by proof of stake, and it's inside of a Cosmos SDK instance. CosmWasm has some interesting differences between its smart contracting level and EVM. Won't go into it. Cosmos Hub, it's the Atom chain. It's the blockchain that was launched as the first Cosmos SDK chain. It's sort of the proof of concept for Cosmos SDK chains, but it's also an important part of routing. So in this world where we have thousands, if not hundreds of thousands of chains, it's meant to be sort of the hub for that routing aspect. It also provides interchain services like security that I mentioned a second ago. So the Atom validator set can be used to secure multiple blockchains. Also relayer subsidies to make sure that the IBC packets get relayed. And then Atom monetary policies. So if you're familiar with the meme like ETH is money, the purpose of ETH is to act as the money for the Ethereum ecosystem. Atom acts is a similar way. Atom as money is the sort of base currency for the Cosmos ecosystem. And DeFi primitives, as well as public goods funding. So Atom's existed and paid for all of the development of all of this public goods infrastructure that's necessary for building application-specific blockchains, Tendermint, Cosmos SDK, IBC, CosmWasm, Ethermint. So it's a way of sort of coordinating and paying for this public goods work. Other applications, Osmosis is a DEX, Stargaze has NFTs, Region Network is for carbon markets, Akash is for a compute market like Amazon Web Services, Gravity Bridge Chain is a bridge to Ethereum, Secret Network is for private smart contracts, Crypto.com is a hybrid central exchange and decentralized exchange. Terra, rest in peace, is kind of a DeFi casino that we're all probably familiar with the story. Celestia is a roll-up data availability chain for scalability of shared state virtual machines. Evmos is the EVM chain that I mentioned, the sort of Ethereum on Cosmos. Juno is a CosmWasm chain, and Desmos is social media. Phew, okay, now we can go back to questions. So would a solo machine, or in this example, your signature, would act like a trusted third party, but the users get to decide whether they trust the solo machine or not? Yes, so the blockchain, if configured the way the Cosmos Hub is, for instance, will accept IBC packets from any blockchain. And it'll just say, hey, this blockchain exists. It has a solo machine as its client instead of Tendermint as a light client. That's interesting. And they also just said that they sent over 100,000 tokens called Billy. So now on the Cosmos Hub, there would exist 100,000 Billy tokens, and that denom would be basically IBC / and then the port and channel of that connection, which is connected to that solo machine Billy client chain, and then the actual name of the denom. So those tokens exist on the hub. Does anybody want to use them? Is anybody willing to buy them? That's a question for the users. I'm able to tell that they came from this WordPress instance. Have I decided to think that they're valuable or not? That's absolutely up to the user to sort of trust. But the blockchain itself is willing to sort of say, like, it follows the protocol, so it does exist in the world. Don't really know whether you care about it, but they were willing to pay the necessary gas fees to create a transaction. So here he is. Jonathan.
Hey, Billy, thanks for the session. I was just wondering, what's the performance profile of Tendermint, I guess, relative to other prominent consensus algorithms? And also, are there any prominent ABCI compatible consensus algorithms that aren't Tendermint?
Sure. So there's been a number of blog posts, research projects that have tried to sort of number crunch or get the transactions per second on Tendermint. It's highly dependent, though, of course, on the content of the transactions, as well as the size of the validator set. So, some people are trying to see, is it possible to maintain whatever transactions per second while increasing the validator set to over 1,000? Or what's the sort of max number of transactions per second when you have any size validator set? And it's much easier to have higher throughput on a smaller validator set. There's a project called Crescent, who I think is doing something like 10 validators because they want to have a centralized exchange-esque order book, and that requires really, really fast transaction processing. I have seen estimates of thousands of transactions per second for Tendermint. And the Tendermint team always talks about how nobody has run into the limits that would require them to make some of the changes to the lowest hanging fruit that would really increase the number of transactions per second for Tendermint. And so we haven't sort of seen anybody working hard on optimizing the vertical scalability of Tendermint at this point. We mostly see people with between 50 and 200 validators inside of a validator set with something around 6-second block times with, you know, the order of dozens to hundreds of transactions per second.
Sweet, thank you.
Thomas Greco.
Hey, Billy. Yeah, thanks for this. This is really good. Impressive. It's a long time. So could you explain a little bit about how like Celestia works?
Sure. So I'm not a Celestia expert, but my understanding of it is that in the world of rollups, you have this really big problem, which is collators. So a rollup is essentially like an off-chain blockchain, I like to think of it, where a bunch of people are pretending like it's a blockchain, but instead of like requiring them to be honest or punishing them for not being honest, you can just sort of take all of the activity that's, you know, taken place, collate it into a big stack of proof of what's going on over here, and submit it back to a network like Ethereum, where they have essentially, it's similar to a light client. You know what I mean? You provide all this proof and say, hey, this is what's going on in that off-chain application. Is that actually legit or not? And that, like, is that legit process might be a zero knowledge proof, or it might be sort of a validation game, which is like, hey, I put it on there, and now there's 3 days for somebody to come and like call my bluff. This isn't really what's going on in this roll-up scenario. And that's a general way that like roll-ups are able to have a bunch of, you know, what's otherwise like an off-chain process with tons of transactions that only periodically need to hit the blockchain and still have some degree of like integrity that this application is still correct. And this problem of providing that evidence is growing because all of that information that happens off chain, it's really difficult to keep track of it all. It's really difficult to put it in the right format that's necessary to put it back on that original chain to prove that it's correct, or even more so to prove that it's wrong. You know, that's the real danger, is like somebody's put up fake information and you have to gather all the evidence to be like, actually, you're totally lying. And there's very little like incentive to do that. I mean, so there's more and more of this data that's accruing that needs to be kept track of by everybody or by somebody. And so the data availability problem is the fact that this data might not be available. If somebody were to somehow get rid of that one transaction and nobody was able to remember that that transaction happened, all of a sudden this rollup would no longer be able to be proven on that, you know, mainnet Ethereum or something like that. And so the data availability problem is trying to make sure that all this growing amount of off-chain rollup information is always available. So the way that Celestia is approaching it is similar to the way BitTorrent works. The more people who are online and running the BitTorrent client, and for instance, trying to pirate Pirates of the Caribbean, the more available that movie is. You know, each person online might only have a little piece of it. Each person online might have the whole movie, but when you're downloading, you only pull a little bit from each one, and you do this erasure code system that sort of like guarantees that the piece that I got from here and the piece that I got from there are actually part of the same coherent whole movie file. And so as my understanding is that Celestia Network is essentially a process for encouraging, paying, and making available various arbitrary data specifically for rollups to make sure that that data that's necessary for proving that it's correct is always available, plus a bunch of other you know, rollup-esque features to make sure that rollups are able to continue operating. So they also would eventually be like a root of trust themselves, as well as just sort of focused on making that data available for proving that the rollups are running correctly.
Okay, cool. So just a quick follow-up. So how does it, like, how do other blockchains use that data availability layer? Like if
so if I were Optimism or Arbitrum or any of these other blockchains, I would, I think, have a service. I don't know how it would work exactly between them. Celestia would, you know, you need to look into the token economics for the like way that they're incentivizing behavior or where they pay, because that's the devil in the details. But
okay, thank you so much
sure,
for
sure.
that breakdown.
Scott.
Yeah, can you just briefly speak about the state of maturity of all the tooling and the guides and the packages? Like Starport became Ignite, the CosmWasm landed on version 1, the Cosmos SDK, a certain version that's incompatible with other versions. GitHub as a source of truth always, but also the guides, the tutorials, the Interchain site. Can you just kind of speak about the state of maturity and what might be lying to us?
Sure. I mean, it's all open source software. So open source is always sort of a combination of way more than you bargain for and way less than you bargain for, depending on exactly the piece of code, where it's coming from, who's supporting it, et cetera. I don't know if I'd be able to give you like a rating or a coherent sort of like system of like, trust that one, don't trust that one. But a good example that you gave is sort of CosmWasm is approaching a 1.0 release. It has typically lagged behind releases of the SDK by 1 or 2 versions. They have a really conservative upgrade cycle, and the Cosmos SDK is a bit more aggressive. So they'll make a Cosmos SDK release, and then, it turns out that there's maybe like a small bug, so they'll do an update and an update. And CosmWasm was tired of having to follow those, what they consider like pretty substantial updates that should have been like patch updates. So they take a very conservative approach. Only once the Cosmos SDK is a couple versions ahead do they consider it stable enough to update CosmWasm. So that's why you see CosmWasm currently in sync with the 0.45 of the Cosmos SDK, whereas the SDK is just release 46. Last year, you would have seen Region Network as the primary Cosmos SDK team. They still work on the Cosmos SDK, but in the last year, the product ownership has shifted towards Interchain GmbH under Marco. And in the middle of that transition is when they were expecting to make the release of Cosmos SDK v0.46. Of course, everybody's always trying to squeeze in things last minute, and so they kept delaying when 46 would get released. And then halfway through this year, which was already 3 or 6 months later than the release, they realized that the upstream dependency tendermint had a bug in it, and so that had to sort of go through a whole nother release cycle. So in terms of like expectations around timelines and releases, it's always hard to tell. It's hard to tell in all software development. But just to give you a bit more of like a idea of the moving pieces and the players involved would probably give you your own ability to sort of gauge what degree of reliability any software is at. There's sort of a separation of the Tendermint team, which is spread between Informal and IG, and has a council at the ICF that sort of determines the roadmap and the release cycle. Downstream from that is Cosmos SDK, which is currently running Tendermint 34. Cosmos SDK just released 46. They're working on a relatively minor update for 47, but they're trying to get it to a point where they no longer have a single Cosmos SDK version that every chain needs to update from. They want to get it to where there's basically a 1.0 Cosmos SDK that almost never updates, and then all of the updates happen at a per module basis. So each module will have its own Go mod file, and the Cosmos SDK will have a separate Go mod file, and that'll create like a much easier system of compatibility checking, because no longer is it the entire blockchain that has to be in sync with each other. It's just the modules on a pairwise basis that you need to make sure are sort of coherent between each other. 47 is likely to come in the next month or two. And then, like you mentioned before, CosmWasm's on this 1.0 stable release. It's on 45. Apparently, they're considering skipping straight to 47, but I don't really believe that. I haven't talked to them directly about this. I imagine they probably update to 46 in the next year or so. Ethermint is on, I'm not super close with the Ethermint development process or cycle. IBC releases really often, really frequently, and they have a few different like branches depending on the features that are involved, because they've started releasing more and more application level modules, things like interchain accounts and the controller module for interchain accounts, the fee middleware module, which is the way that you add the payments to the IBC packets. The IBC team is mostly located inside of Interchain GmbH. There's also the IBC Rust team inside of Informal, but the IBC Rust team is mostly involved with building the Hermes relayer, which is built in Rust. So they need to have IBC abstractions that are all written in Rust. There's two big relayers out there. There's the relayer Hermes in Rust, and then there's the Golang relayer. Hermes is at Informal. Golang relayer is at Strangelove, which is Jack Samplin's company. Hermes is by far the most used in production. The Golang relayer is used in a lot of testing frameworks, and it's now made an emphasis to really support the substrate ecosystem that now has IBC. And so they expect to be more used in like SDK to substrate type network relayers, but it's kind of a arms race between Hermes and the Golang. It's good, healthy competition, I think. But they both release frequently. Scott, I don't know, is there any more specific question you have about like state of the software or what sort of integrity?
Maturity of the docs and what's truth and not truth, like, before you get into details. But yeah, giving that overview of who are the players and where the pieces interconnect is fantastic. Appreciate it.
Sure. Yeah. I mean, I think every team has a rule to not make a release without docs included in it. And the docs are almost all standard built in the same process and auto deployed to GitHub pages using like the same skin. But you know, it's mostly engineers who are updating the docs inside of Markdown files, and there's not very many people who are, you know, cruising the docs themselves, like the distributed version of it. So I feel like I'm constantly finding like small nitpick bugs and like like aesthetic mistakes and the way the docs work. But I'm generally like go to the docs first. If I can't find what I'm looking for in 5 minutes, go to the code. So I don't know if that's a answer to that question, but that's my general framework.